Hi everyone, this video is an explanation of the questions from the week 13 recitation handout. So I'll get right into it. The first question in the handout was, which one of the following pure substances will have hydrogen bonds between molecules? So the key word there being pure substances, so that's going to be hydrogen bonds just between only these molecules for each of the various choices. So if you remember, to have hydrogen bonds, the molecule is going to need to have either a fluorine, oxygen, or nitrogen with a hydrogen bonded to that atom. So you'll need to see one of these three bonds within the molecule in order for the molecule to be able to bond with another of the same molecule. So in order to see if we have any of those bonds in any of these molecules, we'll first draw each of the molecules. So here we have trimethylamine for A, a nitrogen with 3 methyl groups, so each of the atoms bonded to the nitrogen is a carbon, so there's no NH bonds there. The next molecule is dimethyl ether. So again, each of the atoms bonded to the oxygen are carbon atoms, so no OH bonds there. The next molecule is ethanol. So 2 carbons and then an OH. So here we do have that OH, so this could potentially hydrogen bond with another ethanol molecule, like that. So that one can hydrogen bond with another ethanol molecule. Here we have fluoroethane, so 2 carbons with the fluorine. Here the fluorine is bonded to carbon. We need it bonded to hydrogen. So that one's out, and then HI, hydrogen iodide, there's only one bond there between iodine and hydrogen. That's not one of the 3 possibilities, so our answer there is C. Moving to question number 2, which is similar, but now it wants to know of each of the pairs of these molecules shown, which can form hydrogen bonds between them. So again, at least one of these molecules is going to need to have a fluorine hydrogen, an oxygen hydrogen, or a nitrogen hydrogen bond in order to act as a hydrogen bond donor. So as long as one of the molecules has one of these 3 bonds, it can act as a donor, and then it will need a lone pair of electrons to act as an acceptor. So as long as we have one donor and one acceptor in the pair here, then the molecules can form hydrogen bonds between the 2. So here we have HCl and HI, hydrogen chloride and hydrogen iodide. Neither of these have one of these 3 bonds, so that one is out. The next one, B, is methanol and ammonia. So we have CH3OH. So in methanol there is an OH, so that can act as a hydrogen bond donor. We also have ammonia. So there's 3 NH bonds there, so that can act as a hydrogen bond donor as well. Both the oxygen and the nitrogen have at least one lone pair. So the oxygen can act as an acceptor, and this hydrogen on the nitrogen can act as a donor, or any of the other 2 hydrogens. Or this hydrogen connected to the oxygen can act as a hydrogen bond donor, and the nitrogen can be an acceptor. So that one does have the possibility of forming hydrogen bonds between those 2 molecules. We'll just quickly go through the rest of these 3 here. So the next one, C, is methane. So CH4, carbon in the center with 4 bonds to hydrogen, and then H2O. So water is capable of being a hydrogen bond donor or a hydrogen bond acceptor. It has an OH bond and the oxygen has a lone pair, but there's nothing for the OH bond to donate that hydrogen bond to in methane. So that one is out. The next is SO2 and CH2O. So SO2 looks like this. So here there's no FH, OH, or NH bonds. And then if we draw CH2O, that looks like that. So this is formaldehyde. Again, there's none of these three bonds. So neither of those two molecules can act as a hydrogen bond acceptor. The final one here, H2 and O2. Again, none of those three bonds in either of those two molecules, so that one is out. That leaves us with B as the correct answer for number 2. Moving to number 3, it says write the chemical formulas for each of the molecules below and identify the functional groups present in each of those molecules. So first we'll just come up with the formula for each of these molecules. So counting up the carbons first, there's 1, 2, 3, 4, 5, 6, 7, 8. It's going to be C8. Next we'll count up the hydrogen. So there's 1, 2, 3 hydrogens here, 4, 5, 6, 7, and 8. So 8 hydrogens in that first molecule, and then 1, 2, 3 oxygens, so O3. So the formula for this first one is going to be C8H8O3. Some of the functional groups that are in here, so a functional group you can identify basically as anything that's not just a single carbon-carbon or carbon-hydrogen bond. So things like this, or this here. So this is OH, so that is an alcohol. So it's a carbon singly bonded to an oxygen, singly bonded to a hydrogen. Here we have a carbon singly bonded to an oxygen, which is singly bonded to another carbon, so that is an ether. Over here, there's a carbon double bonded to an oxygen with a hydrogen on one side and a carbon on the other side of that central carbon, so that's what's called an aldehyde. And then this ring in the middle, the circle represents alternating double and single bonds. So that is what's known as an aromatic system, or aromatic group. So those are the 4 functional groups that are present in molecule A here. Moving on to the second molecule, seen in B, we'll first start with counting our carbons. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's C13. Count the hydrogens next. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 hydrogens. There's 1 nitrogen and 1, 2 oxygens. So the formula for the molecule shown in B here is going to be C13H13NO2. So now we need to identify what functional groups are present here. And as I said, for A, a functional group is basically going to be anything that isn't a carbon-carbon single bond and a carbon-hydrogen single bond. So here we have a carbon-carbon triple bond. That's going to be an alkyne. So you have an alkyne anytime there's a carbon-carbon triple bond. Again, we have this aromatic group where we have the alternating single and double bonds. Here it was represented by this circle. Here it's shown as the single and double bonds. So that is an aromatic system. We also have over here a carbon-carbon double bond. So that is an alkene. We have a carbon double bonded to an oxygen, and then on one side of that carbon we have another carbon, and on the other side we have an OH. That's what's known as a carboxylic acid. And then here we have a nitrogen with two hydrogens singly bonded to a carbon. That is an amine. So an amine can either have 3 single bonds to carbon, 3 single bonds to hydrogen, or any combination of single bonds to carbon and hydrogen. Those are all amines. Moving on to the final one here, letter C. We'll first start off counting our carbons again. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the formula there is going to be C18. We'll count up our hydrogens. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So H27. Here I've just made a dash where each of the hydrogens are to keep the image a little bit neater. But each dash represents one hydrogen, so each of the carbons I filled in the number of hydrogens to make each carbon have 4 bonds overall. So this molecule also has 1 nitrogen and 3 oxygens, so 1, 2, 3. So we'll look at the functional groups. So like we saw in A here, we have this C single bonded to an OH. That's what we said was an alcohol. We have another ether, a carbon singly bonded to an oxygen with another single bond to another carbon. That is an ether. We have the aromatic group again, the 6-member ring with the alternating double and single bonds. So it has an aromatic group. Here we have a nitrogen connected to 1 carbon, a hydrogen, and then a carbon with a double bond to an oxygen. So that is going to be known as an amide. So it's different from the amine that we saw over here. Here it was singly bonded to just a carbon. Here this nitrogen is singly bonded to a carbon, but that carbon is also double bonded to an oxygen. When you see that pattern, that's going to be an amide, and that's different from an amine that we saw in B. And then the final functional group, again, that's something we saw in B, was that carbon-carbon double bond. That's what we said was an alkene. So the formula for C again is C18H27NO3. These are the 5 functional groups that are present. So these are the formulas and functional groups for each of the molecules shown for each of the 3 parts of problem number 3. Question number 4 asks, what forces hold 2 DNA double helix strands together? So a DNA double helix is composed of 2 strands of DNA. Which of these 5 forces holds those 2 strands together? So the options here are anion-cation bonding, hydrogen bonding, ion-dipole bonding, covalent bonding, and dipole-dipole bonding. So a few of these aren't technically types of bonding. So ion-dipole bonding, dipole-dipole bonding, those are intermolecular forces, so forces that bring molecules together. This could technically be thought of as ionic bonding. So it's probably best to look at what two DNA double helix strands look like next to each other. So just to save some time, I've drawn this picture ahead of time. So here we see two strands. So I've drawn it with each of the four different bases: adenine, thymine, guanine, and cytosine. So we have the phosphate ribose backbone along the side here connecting to each of the bases. So on the right we have the thymine and guanine, and then on the left here we again have the phosphate ribose backbone. So the ribose sugars are shown here in orange and the phosphates are shown here. I've left some of the atoms out just to make it a little bit cleaner. But then we see adenine and cytosine on this side. So right now these two strands are currently unconnected. But when you have these matching pairs, so adenine and thymine and cytosine and guanine, those two base pairs always pair with one another. And the reason for that is because when they come in close contact with one another, this nitrogen on adenine can donate a hydrogen bond to the oxygen on thymine, and the NH bond on thymine can donate a hydrogen bond to the nitrogen on adenine. Similar for cytosine and guanine, this nitrogen can act as a hydrogen bond donor. The carbonyl on guanine can act as an acceptor. This NH and this NH on guanine can both act as hydrogen bond donors and donate to the acceptors on cytosine. So there's two matching sites on adenine and thymine. There are three matching sites on cytosine and guanine. So those two, A and T and C and G pairs always match with each other. And the reason is because the number of hydrogen bonds that are between them. So if we look back at our answer choices, we can see that hydrogen bonding was B. That is the answer. That is the force that holds the two strands of the DNA double helix together. Moving to number 5. It asks which, if any, of the following features is common to soaps, detergents, and phospholipids. So the choices are shown here. They're all fatty acids, they all contain phosphate groups, they all contain polypeptide chains. Or D, their function depends on the dual polarity of the molecules. So for this problem, it's probably best to see what some of these molecules look like. So soaps, detergents, and phospholipids. So a soap, one example of a soap is sodium stearate. So this is a common soap that you probably have used before. So a stearate, it comes from stearic acid, so that is a carboxylic acid with 18 carbons. So if we draw that out, (18 carbons with the carboxylate. So when you deprotonate the carboxylic acid, it becomes a carboxylate. So that is sodium stearate. So that is a common soap molecule. So if we look at something that would be a detergent, things called branched alkyl benzene, sulfonate. So I'll describe what each of those things are relative to the molecule that I'm drawing here. So this is the alkyl part. This is the benzene ring, the aromatic system that we saw in the previous problem, and all these various chains are the branched portions. So these are the branched alkyl benzene, And then this bottom part here with the 3 oxygen bonds to this sulfur is the sulfonate. So this is an example of a detergent. So the fourth possibility is the phospholipid. So I need a little bit of extra room here. So a phospholipid is comprised of 4 parts. So one is typically glycerol. So glycerol has 3 carbons, and on each carbon is an alcohol. So this is what glycerol looks like. The second of the 4 parts is a phosphate. So the phosphate comes from phosphoric acid, which is what we see there. The third part is 2 fatty acids. So a fatty acid is just a long carbon chain carboxylic acid, so something like stearic acid, which we saw when we were describing the soap molecule. So something kind of like that, that's stearic acid. It'll have 2 of those, and then the fourth component is typically some small molecule. This can be a couple different things. We'll use choline here, which is a transmitter. So choline, and that looks like this. So an alcohol with a 2 carbon chain, and then a nitrogen with 3 additional methyl groups. These are the 4 parts that comprise a phospholipid, and they are connected like this. So you have your phosphate with the small molecule connected to one of the oxygens of the phosphoric acid, connecting to this hydrogen. So we have our choline over here. So this positive charge neutralizes this negative charge on the phosphate, and the third oxygen of the phosphoric acid that was singly bonded connects to glycerol. So here we have our 3 carbon 1, 2, 3 from glycerol. This was one of the OHs. We have a second OH there, and our third OH is there. So to each of these, we will add one of the 2 fatty acids. So be like that. I'm not going to draw all the carbons, but you get the idea. That's where the fatty acid would connect, and similar for the second one. So again, we have our phosphate portion, which is connected to our small molecule. Here it's choline. The phosphate is also connected to glycerol, and then through the glycerol we have connected to fatty acids. So looking at each of these, so we have our soap, our detergent, and our phospholipid over here. So there's a couple commonalities that we can see here. All 3 of the molecules have this long hydrocarbon chain. So here in the soap, here in the detergent, and from the fatty acids in the phospholipid. They also have an ionic portion. So here the negative oxygen and the positive sodium. The negative oxygen and positive sodium here. And then in the phospholipid we have the negative oxygen and the positive nitrogen. So If we look at our answer choices, it's going to be D. Their function depends on the dual polarity of their molecules. You have the long nonpolar portion present in each of the molecules, and the ionic portion, which is also present in each of the molecules. So, looking at the other answer choices, they all contain fatty acids. That's not necessarily true. Detergents don't always contain fatty acids, so that is wrong. B states that they all contain phosphate groups. That's not true. Soaps or detergents, neither of those contain phosphate groups. And C, they all contain polypeptide chains. None of the three that we've drawn contain a polypeptide chain. So D is that their function depends on their dual polarity. Moving on to problem number 6. It asks which is likely to be the strongest intermolecular force between difluoromethane molecules. So that's going to be between two molecules of difluoromethane. So if we draw each of those molecules, let's draw two of them. Which of these intermolecular forces is going to be the strongest? So there's a few that we can eliminate right off the bat. There's no ions in that molecule, so we can eliminate D. There's also no fluorine-hydrogen bonds, so we can eliminate C as well. There won't be any possibility of hydrogen bonding. So London dispersion are induced dipole forces. Those are going to be present in any molecule, so that is something that will be a possibility. And then we need to determine whether there's going to be a dipole in this molecule, which would of course mean there's a dipole in this molecule as well. So if we look at each of these bonds, the carbon-fluorine bond is going to be a fairly polar bond with the positive portion at the end of carbon, with the negative concentrated on fluorine. Fluorine is the most electronegative atom. So each of those will have a bond dipole, so that'll give this molecule a molecular dipole overall, with the positive portion over here pointing towards the fluorines. So you may ask, what if you drew the molecule like this, with the fluorines facing opposite one another? You may think that the bond dipoles would cancel, since now they're directly opposite, but this is just an illusion of drawing this molecule in two dimensions. If you were to draw the molecule as would actually exist, it is a tetrahedral molecule. So we'll draw one fluorine up, a hydrogen. So these molecules are in the plane, but then this fluorine will draw with this wedge indicating that it's coming out of the page towards us, and this dashed bond representing the hydrogen, with the dash indicating that it is going away from us into the plane of the paper. So then when we draw these bond dipoles again, we can see that they aren't actually directly opposite one another. They're still at slight angles, so the molecule still does have a molecular dipole. So this does have a dipole, which of course means that this has a dipole. So dipole-dipole is present. Dipole-induced dipole is also present, but it asks which is the strongest intermolecular force between those two molecules, so that is going to be dipole-dipole. That is the strongest, even though each of these three are all present there. Moving on to the final problem in the recitation handout. It asks what is the strongest type of intermolecular force between solute and solvent in each solution. So here we have the solute on the left, and that is the thing that is dissolved in the solvent, which we have shown on the right here. Each thing is in the solvent. And we also have a ranking of the intermolecular forces. So ion dipole being the strongest and dispersion forces being the weakest. So we want to know what's the strongest type of intermolecular force between each solute and solvent. So in order to do that, we'll have to see what forces are present in each of these molecules. So starting with A, cesium chloride, that is a salt. So cesium plus Cl minus. So that's going to be a possibility of either ion dipole or ion-induced dipole. It depends on water. So water, which we've seen drawn several times, we know that it has a molecular dipole. So for A, it is going to be ion dipole. Moving on to B, we have methanol and tetrachloromethane. So if we draw our methanol molecule, we have a CH3OH, so there is a potential for hydrogen bonding, but the molecule definitely has a dipole. It's asymmetrical and it has an oxygen, so the dipole is going to look something like that. And as I said, there's an OH bond, so it has the potential to act as a hydrogen bond donor, as long as there's something that can accept in the other molecule. So CCl4, that's a carbon with 4 chlorine bonds, so each of those bonds, dipoles, cancel one another, so this is a non-polar molecule, and chlorine is not an atom that can accept a hydrogen bond. So the only forces that this one can interact through is induced dipole. So B is going to be dipole, induced dipole. All right. Moving to C, we have dimethyl ether, which I'll draw here. So 2 CH3 groups connected to the central oxygen, that's dimethyl ether, and that is in water, which is similar in structure, but instead of 2 CH3 groups, we have oxygen bonded to 2 hydrogens. So since we have an oxygen bonded to a hydrogen, you can have hydrogen bonding as long as you have a hydrogen bond acceptor, which we do in the other molecule. Oxygen there has a lone pair, so those two can interact through H bonding, which is the second of the strongest of the intermolecular forces. There's no ions present in either of those two, so hydrogen bonding is going to be the strongest force that they can interact through. Moving to D, we have neon, so just the neon gas monoatom, and then water. So since neon is a single atom, it's not going to have a possibility of having a dipole, so the only force that neon can interact through is induced dipole. And water, as we've said earlier, right here, that it does have a dipole. So the strongest force that these two are going to be able to interact through is the dipole-induced dipole, because only water has the dipole of the pair. All right, moving to the final choice E here, it is between nitrogen and butane. So nitrogen If we draw that, looks like that. Two nitrogens triple bonded to one another. There is not going to be a dipole there. Both of the atoms are the same, so there's no difference in electronegativity. So induced dipole will be the only possibility for the N2 molecule. And then we have C4H10. So C4H10. I won't draw all the hydrogens. I'll just draw them as the little wedges there. So all of those CH bond dipoles are going to cancel one another, and all of the carbon-carbon bonds have no dipole. So this is going to be a nonpolar molecule as well, meaning that it can also only interact through induced dipole. So E here is dispersion. So dispersion is the same as induced dipole, or you may hear it referred to as London forces. Those are all the same, and they refer to the weakest intermolecular force. So I believe there was an error on the key that was initially posted saying that, I think it was B was ion dipole. There's obviously no ion in B, so that was an error in the key which has been corrected, but these are the correct answers for the final question in the week 13 recitation handout.